Hello guys! Today I'll talk about vapor recompression distillation, or heat pump. In conventional distillation processes, the bottom stream is always hotter than the top stream because in the bottom we have the less volatile compounds and in the top we have the more volatile compounds. Thus we cannot reuse the energy. What if we compress the top vapor? Maybe it can get hotter than the bottom stream. Then we can reuse that energy in this very clever way. The advantage is that now only a small fraction of the energy is required, but in the form of compressing work. Now let's simulate this case using the iiSE simulator. Start a new project for process engineering. OK. Remove water. And add our compounds. For this case, benzene and toluene. OK. Let's add a source for our feed stream. 100 kilomoles per hour. 95 degrees Celsius. 1 atmosphere. Equimolar composition. And that's it for the feed stream. Let's add the distillation column. 36 stages. A feed on the 18th stage. Okay. Reconnect. Set a reflux rate of 2, a bottoms product of 50. All pressures will be 1 atmosphere. And we are ready, we can simulate this case. All variables were computed. Let's add a sink for our bottom stream. Another one for our distillate. Run again the simulation. Now we have the results. See the heat we need to remove on the condenser and add in the reboiler. Here's the temperature profile. We have 80 degrees at top, 110 at bottom. Now let's make this a vapor recompression distillation case. We remove our condenser and add another feed stream on the first stage. Let's add our condenser as a cooler. Actually, I will add 2 coolers. Connect the streams. Oops, I forgot. I need a splitter for our reflux. Connect the equipment and our reflux. Goes back to the distillation column. I will specify this as our condenser, and this will be an additional cooler. For starters, the condenser will have 0 heat and 0 pressure drop, so essentially it's doing nothing. The second one, 0 pressure drop again, and the temperature will be our top temperature of 80 degrees Celsius. I'll set our split in order to get our reflux ratio of 2. Run again. Results will be essentially the same as before. Reboiling heat of 0.9 megawatts. Top temperature the same. Bottom temperature the same, 110 Celsius. Upper temperature 80 degrees Celsius. Now let's add our compressor. Let's specify the compressing ratio as 3 and an efficiency of 90%. Run again the simulation. Temperature of 117 degrees Celsius. Plenty of temperature to reuse this stream to put heat on our reboiler. We'll do that very simply. Just set that our heat from the condenser will be the same as the reboiling heat using an iiSE formula. By doing this, we add an equation saying the condenser will be the same as the reboiler. This is simple. Just run again and we have our heat pump working. This heat here from the condenser will be exactly the same from the reboiler. Let's rename this to condenser reboiler. From the simulation, it's already working as a vapor recompression system. Now any modification we add to the simulation will take into account this energy reuse. Let's say we change our reflux ratio. I will increase the reflux ratio by reducing the split fraction for the distillate. Now we need more heat on the reboiler and we'll remove more heat on the condenser. Temperature is 112 degrees Celsius for this case. Plenty of temperature to reuse in our reboiler. Let's go back to our original specification, run again. See the energy we need, 0.9 megawatts, and the energy from the compressor is just a fraction of that. That's it. Check out the optimization video on the screen right now and the links on the description below. Thanks for watching.